I'm going to focus on two features of the interactions of sea ice in the ocean that I've explored so far, and how understanding of these processes iterates between observations and models to better understand the system as a whole. And then I'll touch on a little bit some future areas of research, building on these that I'm interested to keep exploring. So first, surface waves are a factor that's increasingly relevant for the Arctic ice formation period in particular, and are generally not represented in climate models. So some recent efforts to include this in climate models have motivated use of observations to understand ice formation in wavy conditions. Second, the Arctic upper ocean undergoes substantial changes throughout the spring to summer in terms of the freshwater budget. Early in the summer, this has substantial implications for the ice melt, where this fresh layer can trap heat near the surface. And then during the transition from the summer to the fall, the distribution of heat around this fresh layer can similarly impact whether or not ice forms and remains during the freeze-up period. So this is just a short video where you can start to see at play some of the processes that we're really interested in. So we can see some small waves from this area of open ocean in the foreground going into these into the ice here. And the form of the waves is rapidly changing, but you can see that they're causing the ice to move around on the surface. So we want to understand how these waves might impact the ice and whether they might drive formation or melt during the autumn season. So thinking about waves has been a big focus of mine and a big interest. And starting with the fundamentals, waves anywhere in the world are going to be a culmination of three factors. So how strong the wind is, the wind speed, how long it blows for, and the distance of distance of water that the wind is blowing over, so the fetch. In a frozen icebound Arctic, as has been typical in the past, the water seals away underneath the ice. So it's essentially a fetch of zero. So the wind can't transfer energy to the ocean to form waves. But as some ice begins to melt and the fetch increases, we've seen larger waves in recent years. And a key point here is that the sea ice edge can act like land in determining the fetch distance for waves to grow. We can specifically see this in observations from wave buoys deployed in the Arctic in open water, so the non-dimensional wave energy, just on the Y here, is the wave height scaled by the wind speed, directly correlates to the non-dimensionalized fetch distance. So the fetch distances are here generally on the order between 50 and 1,000 kilometers. So these observations are following sort of classic fetch laws for open water in other oceans or water bodies. And so this also indicates that the waves in the Arctic are fetch limited much of the time, that they're following these kind of classic laws. So with the loss of sea ice in the Arctic, the fetch area is increasing. And we can see that in these maps of the Arctic sea ice from 1979 to 2012. These are essentially stills from the video we saw earlier. And you can see that there's this much larger area, specifically kind of north of Alaska, so it's a larger fetch. As we showed in a 2018 paper, this is a result of, the result of this is that the wave heights are increasing since the 90s. So you can see that in the top plot here. And that's even as the wind speeds are staying approximately constant. You can see that on the bottom. So the waves are really increasing because this ice covered area is decreasing. So though these maps are showing the ice edge as a relatively distinct clean line, that's actually often not the case, and we'll have large areas of sort of mixed ice cover. So in these areas with low to moderate concentration throughout the melt and formation period, the ice doesn't act like the same hard cutoff for wave growth like land would. So rather, we see that waves can still grow in these areas of low concentration where there's sufficient space between the ice. And with observations, we find that this can be approached as an effective fetch based on the fraction of ice cover. So this figure shows observations from wave buoys in different ice concentrations. That's what's on the x-axis, and the inferred effective fetch for waves to grow to the observed height. And so these distances are typically much smaller than when we were looking at an open water, on the order of tens to maybe hundreds of kilometers. And a fit to these observations then gives us a relationship that we can use to predict or model wave growth in ice. So then we can get wave growth both outside and in ice covered areas, and which we can start to predict. But then we also see the waves propagating through and into the ice, where we expect to see some interesting interactions between the two. So what does that look like? Okay, so first, to think about what waves look like in the ice, I want to think about what waves look like in the open ocean. So this is an area without any sea ice, and I want you to notice the texture of the ocean surface here. So waves are a superposition of lots of different wavelengths. And so in general, we separate this into the longer wavelengths. So the swell, and that's what making the ship kind of rock around in this video. And then also the short wavelengths, the wind waves, which are what's making the surface really choppy. The combination of these different frequencies makes up the wave spectra of the surface. So now I want you to notice the difference of texture in these waves in ice. And immediately looks very different. Notice that the waves are generally very smooth going across the surface. So the wind waves, or the high frequency waves, are generally being damped or reduced by the ice, but not because it wasn't windy. So mostly we see swell or low frequency waves remaining, which are what's propagating through the ice. So the wave period then tends to be higher than in open water. So showing that spectrally, this is just an example from a recent study which showed how the wave spectra was being changed from an open water area through into the ice. You can see that the peaks are largely unchanged, but the high frequency waves out here are being rapidly damped or attenuated in the ice. So just one more video where we can again see the swell propagating through slightly different type of ice. And you can see the waves are moving the ice around, but not in a fully uniform way. They're starting to bump together. And so this can help us start to think about how the waves are interacting with and impacting the ice. And one significant way that waves are important in the Arctic is because of their impact during the ice growth. So this video shows my favorite type of ice, which is this pancake ice. And you can pretty easily tell how it got its name. It has these rounded flows with sort of upturned edges that resembles sort of breakfast pancakes. It's also really cool because it specifically forms when there's waves on the surface, like in this video. So you can see the ice converging at the crests and then bumping together and then diverging in the troughs of the waves. So fundamentally, the ice motion at the surface is a result of the wave orbital motion. So a parcel such as ice at the surface moves back and forth with the passage of each wave. And so this general idea I described for how pancakes form has been understood for a while, so that the pancake ice is a direct result of this orbital motion, which is in opposite directions at the crest and trough of the wave, causing the flows to converge on the front face. We can see that in this video. So if we follow a single pair of flows, we can see them move closer together and then further apart on the wave. And they have a relative velocity, which we refer to here as delta V. In my 2019 paper, I developed a method to be able to observe this relative velocity for the first time in the field. And I found that the motion of this ice is in fact well described simply by the gradient of the wave slope. And this allows the ice to consolidate into these small pancakes. It pushes the slushy ice from the water up onto the sides, causing them to grow thicker. And it grows very different structure than would grow under calm conditions. It can be 2 to 3 times as thick as ice that would grow in the same time under calm conditions. And because of the increasing waves in the Arctic, this type of ice is becoming more common in observations in recent years. And so this motivates being able to include its formation in models. So this formation process that we can understand visually by looking at the surface can also be described by physical relationships. So in collaboration with Letty Roach, I used some observations that I had made to test theories for pancake ice formation and estimate parameters that can be then used in the models. So here I'm showing results from a wave buoy with images of ice growth on the surface. So each point on this plot represents a photo like the one that's shown. So the size of the flows, the measured diameter, we can see has a relationship with the wave characteristics. So this is related based on the tensile strength of the ice. So it's a ratio including the wave height and the wavelength. So then how does this help us better model pancake ice formation? Well, we can predict based on these wave properties during ice formation, the diameter of the flows that might result. As these pancakes start to grow, eventually the flow size also begins to increase by individual pancakes welding or growing together. So you can see an example of that in the photo here. And similarly, we captured the rate that these flows are welding together using photos, which we related to the ice conditions. So the rate of welding in an area is directly related to the ice concentration squared by a constant called kappa. So this kind of empirical relationship currently is neglecting dependence on other factors that might play a role in this, such as sea surface temperature, which we can include in the future. We can in the future define kappa to depend on these parameters as well. But together, these two relationships based on these observations provide a first set of parameters that we can begin to use to describe pancake ice growth and welding in models as a function of the ice and wave conditions, which are already variables that are modeled. And so, yeah, so in fact, this work that we've done to understand wave-related ice processes is being included in climate models. And so new climate models with flow size represented and coupled ocean waves can represent these processes. And these are, I'm showing here results from CSM from work by Letty Roach, where she included flow sizes driven by a wave model coupled with the sea ice model. And so just quickly here, we can see that the typical flow size changes over the year are a result of different wave-related processes shown in this bottom figure. And so welding and pancake formation, which we quantified before, of course, are acting to increase the flow size, whereas wave fracture and breaking are decreasing the flow size. And looking at the impact of these processes Arctic-wide, we can see the impact on predicted sea ice states. This is changes in the thickness. And so some areas have thicker ice in blue, while some have thinner ice in red. And we especially see significant changes in kind of thinning in this North Atlantic region near the ice edge, where it's likely that larger waves could play a role in changing the ice flow sizes and thinning of ice as well. So this is still really a key area for development in sea ice and climate models at the moment. Most have not previously included any form of flow size or coupled a wave model in a way that could allow us to represent these processes. Yeah, so including this kind of observational work will allow us to represent additional feedbacks that may be important with changing climate at the ice-ocean interface. So how long this ice remains at the surface is a delicate balance with the evolving mixed layer dynamics. So globally, mixed layers are often hundreds of meters deep, but in the Arctic, they tend to be much shallower. And we can see that in this figure, which shows all mixed layer observations from August in the summer, when it's typically shallowest due to the fresh meltwater from the summer. And so you can see the mixed layers here typically on the scale of 10 to 20 meters, sometimes even less. And through the summer, the surface is warming from solar heating, but in autumn, this warm water can become trapped beneath the fresher summer halocline. So there can actually be an increase in temperature below the mixed layer. And this is referred to as the near surface temperature maximum. And we can see what an example profile of this looks like. This is from the Beaufort Sea in 2015. And you can see this sort of peak in the kind of 25 to 35 meter range beneath the surface, which, yeah, so this shows this kind of fresher layer near the surface, trapping this heat below, which really does matter for the evolution of the sea ice, or can matter, that's for sure. So then what happens when we combine this reservoir of heat beneath the surface with these waves that we've talked about being more common on the surface? So in addition to mixing from the wind itself, shear in Stokes velocity from waves can drive and increase the upper ocean mixing. So we've seen that these waves can then help to mix up the heat to melt the ice at the surface, in addition to the role that they're playing in the formation here. So this video is from an event in the Beaufort Sea in 2015, where we observed these changes happening. And so during this event, we saw that winds and waves were able to melt the ice at the surface, even under what would typically be formation conditions. And to measure this, we deployed free drifting swift wave buoys. And these showed strong winds over this period. So that's in the black line on this time series, as well as large waves. So the winds were up to 18 meters per second at the peak and waves up to 5 meters. And what I want to particularly draw your attention to is that over this time, we saw from underway CTD profiles, small changes in the upper ocean temperature as well. So these example profiles here show this initial near surface temperature maximum again, initially about 22 meters below the surface, around minus half a degree. And by the end of this event, we saw a deepening and a sharpening with the loss of heat above this layer, with this near surface temperature maximum being eroded. So these changes are coinciding with significant changes that we can see visually on the surface. So we observed almost complete loss of these new pancakes on the surface, about 5 centimeters total. So I put together observations over a larger area where these changes were observed. We had 8 buoys in total, with a heat budget to show how the wind and wave entrainment of this near surface heat melted the pancake sea ice. So I first determined the heat that was lost as a change in temperature, change in the temperature difference from freezing. So you can see that shown visually as the shaded area in this example between these profiles. You can see that deepening mixed layer and eroding near surface temperature maximum. At each point in space, the change in heat content is balanced by the heat fluxes. So we have heat loss to the atmosphere, which we quantified using atmospheric observations, and then to the melt of the ice using changes in the sea ice volume. And then horizontal advection is constrained using the difference in 2 reference frames. And we observed only a small increase accounted for by that. Overall, what we saw is that there's a substantial amount of heat loss from the upper oceans, that's in red. Most of this is actually going into the atmosphere, which we can see in teal here, but a significant portion is also going into melting the ice. And of the total heat loss, about a third was going into the melting the ice, with the rest into the atmosphere, even what we would traditionally think of as freezing conditions with moderately high atmospheric heat fluxes. So as a result, there was ice melt during this event over a pretty large area. And these maps kind of reiterate that change in ice concentration over this area north of Alaska, where the waves are really helping to mix up the heat near the surface. But on the seasonal scale, the ice still forms, although a couple days later. And so this map on the right shows the ice coverage on October 16th, so 2 days after the end of this event. And we see that there's already, again, substantial ice growth. So the results of this work suggests that these large waves observed, which are a new and increasing feature of the Arctic, enhance the mixing in a meaningful way. We've previously assumed that this near surface heat can largely be trapped once the fall comes, but it's clear that that's not always the case. And we're likely to see similar events in the future that might deepen this historically shallow mixed layer in the Arctic and to delay the ice advance in similar ways. This event, I think, also really highlights the importance of the near surface ocean and the stratification for the evolution during freeze up. And this stratification has a really important role throughout the melt as well, when the stratification at the surface is largely forming. So the near surface stratification during the summer is closely tied to the sea ice freshwater budget. So I had the opportunity to study this evolution in detail as part of the team on the Mosaic expedition last summer. And so Mosaic was a year-long expedition. There was a team of scientists observing, kind of tag teaming to observe the Arctic system from the sea ice throughout an entire year. So it was a really large, collaborative and interdisciplinary expedition. I was super lucky to be a part of it and to get to help design and execute observations to help understand some of these questions about what's driving sea ice and upper ocean change during the summer. So to start, I want to address where does this fresh water come from to result in this observed strong summer stratification. And during the Arctic summer, the snow and ice melt are providing a significant source of fresh water. Some of this fresh water accumulates in what we call melt ponds, seen on the surface of the ice in this photo. Can also drain from the ice to the ocean, either below or where it can potentially accumulate under the ice in what we call under ice melt ponds. And it can also drain to the ocean surrounding the ice flows to the leads, which you can kind of see in the foreground here. So this schematic summarizes the key terms in the freshwater budget of the very upper ocean during the Arctic summer. So ultimately, the freshwater that accumulates in the upper ocean is all of the snow and sea ice that melts over the summer, except for what's stored in the melt ponds on the surface. So we were recently able to quantify all these terms with observations from the Shiva campaign, which was a similar expedition in the 90s. So this is work led by Don Perovich, recently accepted in the cryosphere. And so this plot on the right shows the cumulative freshwater input in terms, over the summer. So the total melt input here is in blue. And then the snow and ice melt provided enough freshwater input over the summer to produce in total a 68 centimeter thick layer of freshwater by the end, which is quite a lot. Then partitioning this into ponds and the ocean in green and red respectively, we can see that very little of this remained in the ponds, only about 15%. So the majority of this freshwater is going into the ocean somewhere. So what this ultimately shows is that there's a large freshwater flux into the Arctic upper ocean in really like a pretty small amount of time. This is really only over less than a month in this plot here. But these results don't explain what we can't quite get at here yet is the fate and impact of this freshwater in the upper ocean. And so we got to explore these questions a little more during Mosaic. And so this is just a nice photo, which I think kind of shows some of visually well, I think what we're interested here. So we're looking up through a hole in the ice on the Mosaic flow, and we can actually visually see this freshwater layer. It's about on the order of 0.5 meter thick. And so underneath this ice on the surface, there's this distinct freshwater layer with saltier water below. And you can see the transition, the halocline, particularly well here because of biological material that's trapped at this interface. So the accumulation of this fresh layer under and between the ice obviously has impacts for the ecosystem, which we can see here, but it also impacts the ice, the mass evolution. And it does that at least in 2 ways that that we're working to understand. Okay, so this figure looks at the freshwater budget in sort of a cross-sectional view, so cutting into the ice. And so very, very early in the summer, this snow and sea ice melting on the surface is producing a lot of freshwater. And some of this drains horizontally from the ice where it accumulates in leads between the flows. So the accumulated water in leads can warp substantially, which acts to enhance the melting nearby. Then with increasing permeability of the ice throughout the summer, the fresh meltwater can also drain through the ice vertically. And some of this fresh water can remain relatively separate and unmixed under the ice, particularly in high spots as under ice melt ponds. They're kind of shown schematically in this plot as this black-white, or kind of above this black-white dashed area. So the accumulation of this freshwater can also result in the formation of false bottoms. And so that's actually at this line here, where we get ice growing at this interface between the freshwater and saltwater as a result of diffusional transport of salt and heat across this interface. So starting with looking at leads, a first order motivation for understanding the evolution of freshwater here is that observations have shown that the accumulation of heat in thin layers on the order of 1 meter can result in the enhanced melt of ice. So on the left are observations from prior field campaign from Sheba, which shows over time this fresh meltwater. You can see that salinity is less than 4 here, which is preferentially warmed by solar heating. So the temperatures here on the bottom show relatively warm water. So, I mean, it's not that warm, it's in the order of 1 to 2 degrees, but it actually represents quite a bit of heat here that can substantially melt the ice. And we can see that in this photo. So this is at the edge of the ice adjacent to this layer, and you can see this ledge that someone's standing on as a result of this, what we call lateral melting at the edge. So I made a lot more measurements of this type of structure in lots of different leads last summer to try and characterize the accumulation of this freshwater layer and its impact. So although we've observed this layer a few times in the past, most notably and thoroughly in that example that I just showed, our effort during Mosaic was unique in that it was not only more extensive, but it also included strong collaboration with measurements of other physical drivers and the other parts of the system, such that we can truly start to get at what controls the formation and the evolution of this layer, and also how it interacts with other implications. And hopefully we can start to represent and parameterize it in models. So just love using videos to help us really visualize what these things look like. So this is just from profiling with the GoPro. And hopefully you can kind of see this layer. So there's this sort of brown hazy layer, which is, again, some of this biological material sitting at the interface of these 2 densities of water. And so that kind of allows us to see the transition from the fresh water near the surface to the saltier water below. Sometimes you can see it as a sort of shine, which is the reflections off the halocline. You can also sort of see in some of the ice surrounding, there is a little bit of a structure at the edge, which is indicative of some of this preferential melting that we have. So these layers become especially distinct such that we can actually see them with a GoPro because the ocean is relatively dark. So it has a low albedo. And so this fresh water near the surface is accumulating more heat in the leads where it's exposed. So in this photo, I'm making measurements of this heat accumulating in the upper ocean. I did this largely from a kayak, which is turns out to be a pretty good platform for getting away from the ice edge with minimal disturbance to this thin surface layer. So here I'm using a small castaway CTD, which we used in addition to other instruments to measure these profiles of temperature and salinity on a fine scale. We observed the accumulation and also evolution of this fresh and warm layer throughout the month of July. And so this plot shows the salinity averaged over the upper 7 meters from the castaway on 7 different days. Each of these include about 5 to 10 profiles. And we can see in all of them a low salinity layer as we get close to the surface. We can zoom in to see these with better resolution using observations of made with a different instrument in the upper 1.5 meters. So this shows again salinity on the right, but then on the left we have the temperature relative to the freezing temperature. And on the 4 days that are highlighted here, we can see there is some variability in the heat in these average profiles, but we can see some periods where the heat is building up, as in the shaded region, but it's also not clear that it's as simple of a story or just a linear progression in one direction. So coincident observations of the atmospheric and other ocean changes will allow us to develop and improve parameterizations for how this heat storage in the upper ocean evolves over the summer. And this is particularly important because this level of stratification cannot typically be resolved in climate scale models. So even though it may have large impacts for the ice melts and other parts of the system, we don't yet have a way to represent it. In fact, we can test in models how these some of the changes from these small scale details might have impacts for the sea ice in Arctic Ocean, which we can do with model sensitivity studies. So I ran a model experiment in collaboration with colleagues at NCAR, changing the rate of the lateral melting from the heat in the ocean. So this connects actually both of these processes. So the waves and stratification, which both might impact the lateral melting to explore the impacts on the sea ice. So compared to the default settings in the model, I increased the rate of the side melting by up to 100 times. And interestingly, this actually changes the total melt by very little, only about 5%. Instead, we see that about 60% of the bottom melt, or the melting at the bottom of the ice, is replaced by this melting at the sides. But nonetheless, as a result, this transfer results in feedbacks that actually drastically reduces the sea ice volume. So this shows the average annual cycle of the sea ice volume simulated. So the control is in teal. And then this run with 100 times lateral melt rate is in magenta, where we have about 30% less sea ice mass in the summer. So based on these results, I also proposed and tested a new parameterization, which could improve the representation of this layer and allow us to integrate the observations. So I'm not showing that here, but it's in more detail in the manuscript we have in review. So this is a sensitivity study. We don't really yet have the sufficient observations to know for sure how much the melting should happen from the sides versus the bottom, like whether this 100 times increase, which might sound very high, but might actually be regionally reasonable where there's large surface waves and high surface stratification. But neither of these processes had been included in climate models. So improving this parameterization and improving the lateral melting could be a missing feedback that will change in a warming climate. So during Mosaic, we also observed similarly the accumulation of fresh water under the flow in what we call these under ice melt ponds. So interestingly, these lead to the opposite general effect on the summer ice mass balance. I should start the video. So we can see that here. So you can see that we're on an ice surface with some melt ponds. And as we go down through the ice, you can see that there's some kind of bubbles in the ice here, but we'll go through a sort of hollow space, there's a void space here, and then a slushy layer below. And that's this false bottom, this slushy new ice that's grown during the summer. And here is about a couple centimeters thick. Below that again, here we can see some of the shimmer of this freshwater layer, like we could see in the leads in the GoPro earlier. And we can see that these features are occurring over this wide area of pretty level ice. And so while these features have been sparsely observed in the past, they seemed to be common under level ice in our observations. So we want to understand more about how much they occur, but also largely their impact on the summer sea ice processes. So this especially includes the mass balance, where this false bottom represents the only source of ice growth during the summer. They're also likely to impact a lot of other processes, including gas exchange. This false bottom creates a relatively low permeability layer, but also nutrient exchange with implications for these ice bottom algal communities. You could see in the video some evidence of that algae at the bottom. So we made measurements of these false bottoms in 132 holes and under ice ponds, and of the under ice ponds in particular in 34 holes throughout July. We observed them in about 20% in total of our observations. And most notably in preliminary comparisons of mass balance observations with and without these false bottoms, we suggested it accounts for about a 1-week delay in the ice bottom melt. However, the distribution of these features varies a lot, both spatially and over time. And spatially, we saw these features really concentrated under thin level ice like we saw in that video. So the fraction of these measurements with false bottoms is shown as red in this histogram. And you can see that almost all are concentrated under this ice that's 1 to 1.5 meters thick. We also saw that proximity to this kind of to ridged ice with big keels and topography provides sheltering for these features. And additionally, the overlap of this freshwater input like from melt pond drainage and low mixing are both necessary for these under ice melt ponds and false bottoms to evolve. So these results indicate that these may be, in fact, a common feature of the Arctic summer. And so in addition to the potentially significant impact on the ice mass balance, they also have important impacts for the ocean system. So for example, they can significantly reduce potentially the ice ocean drag and other exchange processes. So here we're just comparing, I'm comparing the observations that we made of false bottom evolution, which are shown as the red X's, with predictions from a 1D model for false bottom growth which we ran with a range of different ice ocean friction velocities. So you can see there's one line here that agrees reasonably well, at least over the beginning of the period. But this requires us to use a drastically lower drag coefficient than has typically been observed in the Arctic. What we think this indicates is that there are mechanisms related to these layers that can become kind of very slippery, which can drastically impact the momentum transfer from the ice to the ocean. So this really motivates doing more work to better understand the impact of these layers at this interface. It can also have big impacts for the under ice algal communities. So we observed this. There was indication of this with rapid die-off of this Melisirus. This is Arctic algae under the ice. And we saw with the emergence of this meltwater layer that rapidly disappeared. So we're planning to explore further other implications of this meltwater layer for this sea ice community, including the Melisir that we can see here. So understanding how these small scale processes may result in feedbacks for large scale changes is especially motivated as the sea ice is thinning. So this is a pretty old schematic, but I think it shows an important point that in addition to these changes we talked about earlier in terms of the area of the Arctic Ocean that's covered by ice, there's also a lot less ice separating the ocean from the atmosphere above. And so as a result, much more of the ice is also what we call seasonal. So we have ice that's melting and reforming each year. So whereas there was only about 50% seasonal ice in 1980, it's been reaching upwards of 75% in the last few years. So this ice that is thin and is melting and reforming each year is much more at the whim of the ocean. And so the role of the upper ocean in terms of the waves and the stratification are really going to be enhanced in determining this evolution. So the future of the ice depends strongly on feedbacks associated with the interactions with the upper ocean. So summarizing the two main topics that presented here so far, this greater open water area leads to more surface waves, and as a result, we see more pancake ice growth. So here, modeling needs to represent this process have motivated use of observations to produce new parameterizations. Second, open water areas in the ice pack can accumulate heat very near the surface that is used to melt the ice. This is really important during the melt season through more standard melting processes where the increased heat is going to melting of the sides, and that can significantly reduce the ice pack. But also we saw that during the growth season, when we're typically forming ice, we can have melt in this sort of wave enhanced way, which can potentially delay the local freeze up. So these are two feedbacks that we don't typically include in climate models. So this work is influencing models and allowing us to improve our ability to predict sea ice in a changing climate. Of course, there's lots of other feedbacks in the Arctic between sea ice and the ocean still to explore. So we're planning to continue to use these sorts of novel targeted data collections motivated by model needs and sensitivity to address some of these issues. So sea ice changes are particularly sensitive to the ice albedo feedback in reality, and largely this is captured in most models, but there's a lot of potential variability that's not yet captured in the model representation. So additionally, ice that forms in shallow coastal regions can have significant amounts of sediment incorporated during formation. And we actually made some of the first time series measurements of this melt and albedo in sediment-laden ice on Mosaic last year. And so this motivates better understanding how the ice is forming with the sediment in it, which then has a feedback again on the albedo and that kind of heat budget evolution. Okay, I think it's been almost an hour. So I'm gonna just skip through some of these slides quickly. There's lots more to explore here about these feedbacks between the variability in the albedo at the surface and the details of what the ice looks like. And in particular, in these areas where we see, as we can see in this satellite image, some areas where there's this kind of dirty ice that you can visually see is darker. And so how that is driving these reductions in the albedo that can absorb more heat. And so understanding the impact of the sediment on the heat budget requires us to understand the really small scale processes of how the sediment is getting entrained and getting into the ice. So just as a final conclusion, so these observations of small scale processes that are motivated by gaps in models, I think have the potential to significantly impact how we understand and adapt to a changing Arctic and changing climate. So thanks for listening. Happy to answer questions.